Hi, this is Gary Rubenstein, and today I want to show you how Archimedes came up with a formula from geometry for the surface area of a sphere, and that formula is 4 pi r squared. And not a lot of people know how to derive this formula, so I'm going to show you how Archimedes did this in a very clever way. And his basic idea was that he started with a regular polygon that has an even number of sides. In this case, this is a 12-sided figure. And two opposite vertices, in this case A and F. It's kind of like the diameter of this thing. And if you take this figure, this regular polygon with 12 sides, and we were to rotate it about its diameter AF there, look at what ends up happening. We will get a figure shape that looks like this. Now this thing is not a sphere, but if the original polygon had a lot of sides, this thing would be approximately a sphere, and the more sides we have, the more it would approach being a sphere. Well, let's look what this thing is. This thing is composed of two cones. You can see on the right and on the left there's cones, and the rest of the figures are frustums of cones, although in this case the middle one's like a cylinder, but it still can be considered a frustum of a cone. So Archimedes' idea is to figure out the volume of this figure and then see what happens as the number of sides of the original polygon approaches infinity, and then that will get him his approximation for the sphere. So this is the figure that he's going to work with. It's a really good idea. In order to do this, he's going to need to have the formula for the surface area of a cone and the surface area of a frustum. Well, the surface area of a cone is pi times r, which is the radius of the base of the cone, times L, which is the lateral height, this side from A to B. And that's not a commonly known formula, I don't think. And I'm going to derive that for you now. And so the basic idea is that every cone, if you cut it along its lateral edge, like in this cone from A to B, if you cut it along the lateral edge and you kind of unroll it, what it becomes is the sector of a circle. And I have here on the side the sector of the circle of the flattened out or unrolled cone. And as you see, if the cone is taller, that angle gets smaller, and if the cone has a real small height, it unrolls almost into a circle itself. And I'm going to use this property to come up with that formula for the surface area of a cone. So here's how you derive the formula. Surface area of a cone is pi times the radius of the base times the lateral height. The idea is this: you have this circle here that I'll point to. This sector of a circle, A, B, B. That's what happens when you unroll this cone. And the idea is this: we know what we know that this original base of the cone had circumference 2 pi r, where r was the radius of the base. But when you unroll the cone, that's what this arc down here is, this from B over to the other B. So we know that length is 2 pi r. This here is r from O to B, that's r. And this from A to B is L. Well, that means this is L also. So L, if you imagine this is a sector of a circle, if that circle were completed, the circumference of this entire circle would be 2 pi L. Well, this is a portion of the circumference of that circle, and it's 2 pi r. So if we divide, if we do 2 pi r over 2 pi l, that will tell us sort of the percent of the circle that we have here. So if we then multiply that by the area of this circle, well, the area of this, if the circle were complete, that this is the sector of, the area of it would be pi times L squared. So once again, this here is sort of the proportion that this sector is of the entire circle, because we know what the circumference of the whole circle would be, and we know what the size of this arc is. So that gives us a percent. If we multiply that by the area of that would-be of that completed circle, well, a lot of stuff cancels out. The 2's, the pi's, this L can cancel out with one of these L's. And we end up with the formula for the area of a cone is pi times r times L. And that's going to be a very important formula that he's going to use later on in his proof. There's one more formula you have to be aware of to follow this proof, and that is the area of a frustum of a cone. And it turns out to be pi times the sum of the bigger radius plus the smaller radius of the two bases times the slant height of that frustum, which is basically from here to here. And I'm going to show you how to derive that formula too from the cone formula that we just got from before. To derive this formula, I'm going to make a simplified picture of what's going on. So just to draw in a pretty ugly cone, I'm going to call half of this is going to be lowercase r, half of this is going to be capital R. I'll call this S, and I'll call this X. Now, because of similar triangles, we could say that R over capital R is equal to X over X plus S. And if we cross multiply, we're going to get this relationship that's going to come in handy later for a substitution. Capital Rx equals lowercase r times x plus s. Okay. Now, to get the surface area of the frustum, we're just going to subtract the two surface areas of the two cones. So the big cone is pi capital R s plus x. Subtract away the small cone, which is pi lowercase r x. Next step is going to factor out the pi just to make this thing easier to see. I'll need big brackets here. R s plus x minus r x. Now here comes the opportunity to do a substitution. Actually, not yet. I'm going to multiply this r through, so I can use regular parentheses. We have rs plus capital R x minus lowercase rx. Here's where the substitution can happen. This capital Rx can be replaced with, here we have capital Rs. The capital Rx can be replaced with lowercase r times x plus s minus Rx. And when you multiply this through, the lowercase rx's cancel out, and we end up with the formula, which is this: r plus lowercase r times s. And
as the
To be continued.